Okay, so we have another definite integral to find here. Evaluate the integral of this function on this interval. And so we might want to think about what that graph looks like. I'm not going to sketch it just so I leave enough space here to work out this problem. But you might go ahead on your graphing calculator and graph what this function looks like on that interval. One important thing to notice is that this function is completely touching or above the x-axis everywhere on this interval. So our value of this integral truly represents area and should be a positive number. Also, at the right endpoint, when x is 3, this function has a big output. So I should expect a pretty big answer when I evaluate this integral here. All right, so when I do this, I don't know the antiderivative of this function. Don't know the antiderivative of this function. So I'm going to have to think through how I find an antiderivative when it's one I don't know. And really at this point for Calculus 1, we have one technique for finding an antiderivative when we don't already know it, and that is U-substitution. So we're going to do a U-substitution here. Because we're doing that with a definite integral, there are a couple of details to pay attention to here. So for U-substitution, you think about what you might let U equal so that your du is accounting for all the rest of the variable parts of the expression here. So this one should be pretty obvious. We did U-substitution last week. Should be pretty obvious if you got through all of that okay, what to let U equal. I have an inner function here, x squared function inside the exponential function. So that's what we want to let U equal. And our du would be 2x dx, which accounts for all the variable parts of this. I do have this extra 2 here, which I need to deal with. So we talked about how to do that. You can divide through by 2. So you would have 1/2 du equals x dx. And my x dx is accounted for here. My x squared accounts for this. All right, so we're doing a U-substitution, this time with a definite integral. So we are going to have a little bit to be careful about here. But let's go ahead and do the substitution here. So in place of the x dx, I'll have 1/2 du. I'm going to put the 1/2 out front, du. In place of the x squared, I'm going to put u. All right, now I need to be a little bit careful here because these numbers at the original problem, limits of integration, were x values. This is an integral in terms of x. This is an interval of x values. At this point, and with this notation, this is indicating an interval of u values, So it would be important here to distinguish between these x equals 0 to 3 values that we started with here and what the appropriate values should be for u. At this step, my entire integral should be in terms of u and not x. So I need to figure out what these limits of integration should be for u at this step. All right, so I'm going to use my x values, and I'm going to use my original U-substitution here. So when x equals 0, using my U-substitution, my u is x squared, so 0 squared is also 0. So my lower limit of integration, when x is 0, is going to correspond to a u value, which also happens to be 0. That's a u value. All right, and then at the other end of my integral, when x is 3, my u is going to be 3 squared, or 9. So my upper limit of integration here should be 9. Those are u values. When you have a du differential at the end, your limits of integration here should be u values. Whatever this letter is here, these values here should correspond to that same letter there. All right, so once I've dealt with that though, then I can use fundamental theorem of calculus and do what it says. So provided this function, e to the u, that's continuous everywhere, is continuous on our interval, then I can find an antiderivative of the function. I'll have this 1/2 factored out front. Any antiderivative of this function, so I'm going to use e to the u plus 0 because that's easy, evaluated from 0 to 9. And so I'm going to be putting those u values in here as well. 1/2 e to the 9th minus e to the 0. All right, e to the 0 is just 1, so you can clean this up a little bit if you want and rewrite this as 1/2 times the quantity e to the 9th minus 1. That would be an exact form. And if you want a decimal approximation, you can plug that into your calculator, get a decimal approximation. You should get about 5,401. So we said pretty big number. That is a pretty big number. So that should seem pretty reasonable if you think about the graph of this function over this region. All right, but big deal thing here when you're doing U-substitutions with a definite integral, to remember to change those limits of integration so that those are in terms of whatever variable you converted to here, u. So make sure you've got x limits of integration at the beginning when it's a dx integral, u limits of integration here when it's a du integral. And then you can just finish the problem like that in terms of u. All right, we'll look at some other examples using the second fundamental theorem of calculus.